Welcome to G Fun Facts Online. The world is facing a monumental challenge. How do we power our modern lives without destroying the climate? We need vast amounts of clean, reliable energy, and we need it now. For years, nuclear power has been the elephant in the room. A carbon-free powerhouse, but one haunted by the specter of long-lived radioactive waste. The conventional approach, using fuel once and then designating it as high-level waste to be stored for tens of thousands of years, has been a tough pill for the public to swallow. But what if we could change that narrative? What if the next generation of nuclear reactors didn't just produce less waste, but actually consumed the waste we already have, turning a multi-generational liability into a valuable asset? This isn't science fiction. This is the revolution happening today in next-generation nuclear design, and it's set to redefine our energy future. Let's dive into the new breed of reactors that are making this possible. At the forefront are what we call Generation IV reactors, a quantum leap beyond the designs that power most of our world today. They are engineered from the ground up for superior safety, better economics, and most importantly, a sustainable fuel cycle. Perhaps the most radical of these is the Molten Salt Reactor, or MSR. Forget the solid fuel rods you might picture. In an MSR, the nuclear fuel is dissolved into a liquid, typically a molten fluoride or chloride salt, which also acts as the coolant. This fundamental shift from solid to liquid fuel is a game changer. In a traditional reactor, as fission occurs, byproducts build up inside the solid fuel rods, eventually poisoning the chain reaction and forcing the entire fuel assembly to be replaced, even with plenty of usable fuel left. But in an MSR, the liquid fuel can be continuously circulated and processed. Think of it like a dialysis machine for the reactor. Fission products can be filtered out online, while the fuel keeps circulating. This allows for a much more complete burnup of the fuel, squeezing vastly more energy out of the same amount of uranium and dramatically reducing the final volume of waste. Even more exciting, MSRs can be designed as burner reactors. Their mission? To consume the long-lived radioactive elements, like plutonium and other actinides, that make conventional nuclear waste so problematic. Some MSR designs can even run on the spent fuel from today's reactors, effectively eating our existing nuclear waste. Companies like TerraPower, co-founded by Bill Gates, are developing the molten chloride Fast Reactor, designed specifically for this purpose. Another fascinating avenue for MSRs is the thorium fuel cycle. Thorium isn't fissile on its own, but when it absorbs a neutron, it becomes a fantastic fuel called uranium-233. The big advantage here is that the thorium cycle produces far fewer long-lived actinides than the standard uranium-plutonium cycle. The waste is mainly fission products, most of which decay to safe levels in a few hundred years, not tens of thousands. Next up is another design focused on extreme safety and efficiency, the high-temperature gas-cooled reactor, or HTGR. These reactors use inert helium gas as a coolant instead of water, allowing them to operate at incredibly high temperatures, often up to 950 degrees Celsius. This high heat doesn't just mean more efficient electricity generation. It also unlocks the potential for nuclear power to decarbonize heavy industries by providing process heat for things like hydrogen production. But the real star of the HTGR is its fuel. It's called TRISO, which stands for TRI Structural Isotropic Particle Fuel, and it's widely considered the most robust nuclear fuel on the planet. Each TRISO particle is a tiny kernel of fuel, about the size of a poppy seed, encapsulated in multiple layers of carbon and ceramic materials. These layers act like a microscopic, ultra-strong containment vessel for all the radioactive byproducts. Even at temperatures far beyond what the reactor would ever experience, those fission products stay locked inside. This makes the fuel essentially meltdown-proof. This robustness allows TRISO fuel to achieve a very high burnup, extracting more energy and thus creating less waste per unit of electricity. Leading developers here include X-Energy, with its XE100 pebble bed reactor, and Ultra Safe Nuclear Corporation. Now, if MSRs are the recyclers and HTGRs are the paragons of safety, then fast reactors are the masters of transmutation. Fast reactors use high-energy or fast neutrons to sustain the fission reaction. Unlike thermal reactors that slow neutrons down, these fast neutrons can split a much wider range of heavy elements, including the plutonium and other actinides that are the most hazardous components of nuclear waste. This makes fast reactors the cornerstone of a closed fuel cycle. You can take the spent fuel from a conventional reactor, reprocess it, and fabricate the recovered actinides into new fuel for a fast reactor, where they are fissioned to generate more power. You effectively turn the most dangerous, long-lasting waste into more clean energy. One leading design is the sodium-cooled fast reactor. TerraPower's Natrium reactor is a modern take on this, cleverly pairing the reactor with a molten salt energy storage system, allowing it to store heat and dispatch electricity when the grid needs it most, making it a perfect partner for intermittent renewables like wind and solar. A demonstration of the Natrium reactor is planned for a retiring coal plant site in Wyoming, showing how advanced nuclear can help communities through the energy transition. Finally, let's talk about a category you've probably heard of: small modular reactors, or SMRs. SMR isn't a single reactor type, but a classification based on size and construction. These are reactors producing 300 megawatts or less, designed to be built in factories and shipped to a site for assembly. This modular approach promises to lower costs, slash construction times, and allow for deployment in more places, like remote communities. The SMR category includes a variety of advanced designs, from scaled-down water reactors like NuScale Power's VOYGR to MSRs and HTGRs. But what is their impact on waste? The answer is complicated. Proponents argue that since many SMRs are advanced designs with higher burnup, they will ultimately reduce the waste burden. However, a 2022 study from Stanford raised concerns, suggesting that due to their smaller size, some SMRs might have greater neutron leakage, where neutrons escape the core and activate surrounding materials, creating additional radioactive waste. Other analyses counter this, arguing that when you factor in thermal efficiency and higher burnup, the waste profile is comparable or even better than large reactors. The key takeaway is that the waste impact of an SMR depends entirely on its specific design and fuel cycle. All these revolutionary reactors are powered by equally revolutionary fuels. We've already touched on TRISO, the poppy seed-sized particle that the U.S. Department of Energy calls the most robust nuclear fuel on Earth. Its multi-layered ceramic shell provides incredibly resilient containment. Modern TRISO fuel can achieve burnups 3 times higher than conventional fuel, meaning vastly more energy is extracted before it becomes waste. But to make many of these advanced reactors work, especially the smaller, more efficient designs, they need a richer fuel. This is called high-assay low-enriched uranium, or HALEU. Standard reactor fuel is enriched to about 3 to 5% uranium-235. HALEU is enriched to between 5% and 20%. It allows for smaller reactor cores and longer-lasting fuel, but creating a reliable supply chain for HALEU is a critical hurdle we need to overcome to enable this new nuclear fleet. The other key advanced fuel type, especially for fast reactors, is metallic fuel. This is typically an alloy of uranium, plutonium, and zirconium. Metallic fuels have excellent thermal conductivity, which helps keep the reactor cool and adds a significant safety margin. But their biggest advantage is their compatibility with a reprocessing technology called pyroprocessing, which is central to closing the fuel cycle. Metallic fuels are also perfect for incorporating the actinides recovered from spent fuel from our current reactors, allowing them to be consumed and destroyed in a fast reactor. This brings us to the ultimate endgame for many of these systems, the closed fuel cycle. This is a fundamental shift in thinking. Instead of the once-through cycle where we use fuel once and then classify it as waste, the closed fuel cycle treats used fuel as a valuable resource. The process starts by reprocessing the used fuel. About 95% of it is simply uranium, which can be recycled. About 1% is plutonium and other long-lived actinides. In a closed cycle, these are also recovered and fabricated into new fuel, typically for fast reactors that can burn them. What's left? About 4% of the original volume, consisting of fission products. While some are highly radioactive, their radioactivity decays to safe levels in a few hundred years, a far more manageable timescale than the tens of thousands of years required for actinides. The key technology to make this happen is pyroprocessing. This is a high-temperature electrochemical method for reprocessing used nuclear fuel. The used fuel is dissolved in a molten salt, and an electric current is used to selectively pull out the uranium and actinides, leaving the fission products behind. A critical feature of pyroprocessing is its inherent proliferation resistance. It doesn't separate out pure plutonium. Instead, plutonium is recovered mixed with other actinides, making it much less attractive for potential misuse. The separated fission products are then locked into a durable ceramic or glass form for permanent disposal. An even more advanced concept is partitioning and transmutation, or P&T. This is the ultimate waste reduction strategy. Partitioning means separating the used fuel into its constituent elements with extreme precision. Transmutation then involves bombarding specific long-lived isotopes with neutrons to transform them into shorter-lived or even stable, non-radioactive isotopes. P&T could potentially reduce the long-term radiotoxicity of the final waste by a factor of 100 or more, dramatically shrinking the footprint and requirements for a permanent geological repository. While P&T is still largely in the research phase, it represents the pinnacle of sustainable nuclear waste management. This isn't just happening in labs. The journey to commercial deployment is well underway, supported by initiatives like the U.S. Department of Energy's Advanced Reactor Demonstration Program. Companies like TerraPower with its Natrium reactor, X-Energy with its XE100, Kairos Power with its Fluoride Salt-Cooled Reactor, and NuScale Power with its SMR are all pushing to have demonstration reactors online in the 2020s, with commercial plants to follow in the early 2030s. Of course, the path forward isn't without challenges. As we discussed, the waste profile of SMRs needs careful analysis for each design. Establishing a secure supply chain for HALEU fuel is essential. The technologies for closing the fuel cycle, like pyroprocessing, are complex and require huge investment to scale up. And perhaps the biggest hurdle of all is public acceptance. For decades, the political stalemate over a permanent waste repository, like the one at Yucca Mountain, has shown that social and political challenges can be just as difficult as technical ones. Building public trust through transparency and demonstrated performance is non-negotiable. The story of nuclear energy is being rewritten. The problems of the past are being met with a wave of innovation that promises to transform nuclear power into a true cornerstone of a clean energy future. Next-generation reactors and their revolutionary fuel cycles offer a credible path to dramatically reduce the burden of nuclear waste, enhance safety to unprecedented levels, and use our fuel resources with incredible efficiency. This journey will be a marathon, but with a new generation of scientists and engineers leading the charge, the prospect of a world powered by abundant, clean, and sustainable nuclear energy is no longer a distant dream. It's about building a brighter, cleaner, and more energy-secure future for everyone.